What's a vector? What's a vector? Well, given that there are lots of kinds of vectors, and you have no idea what a vector is, I'm going to guess that you're talking about Euclidean vectors. Euclidean vectors are a geometric quantity with a magnitude and a direction. They're the kind of vectors that you'll find a lot in those math and physics classes that you're going to fail. Vectors can be used to describe quantities like velocity. In that case, the speed is the magnitude of the velocity, and the direction is where that speed is pointing. There are other vector quantities like force. With a force, there's a magnitude, i.e. how hard I'm pushing or pulling, and there's a direction to the force. In this case, it was in the board or out of the board. That is a quantity with a magnitude and a direction. That is a drawn representation of a vector. Professor Rage, that's just an arrow on the board. How is that a quantity with magnitude and direction? Look here. This arrow has a direction. For the sake of this example, so I don't explode your tiny head, we'll call this north, and we'll call this east. Now look at this. This arrow right here has a length. Let's say it's 7. It has a direction. Given that that's a 45-degree angle, this arrow is pointing northeast. What is this? This is a quantity. An arrow representation of a quantity. It has a length of 7 and a direction northeast. In other words, you can draw a vector with varying lengths, and the varying lengths represent different magnitudes. This has a magnitude of 7 units in a direction of northeast. This is a vector quantity. In the case of diagram representations of vectors, length and magnitude are synonymous. I can create a vector by connecting an initial point A and initial point B, where A and B are points in space. And I can make this vector by starting at the initial point A and drawing an arrow up to the final position B. The connection of these 2 points is now a vector AB. However, vectors do not have a location in space, only a magnitude and a direction. I could draw another vector here with the same magnitude and direction, and the vector notation for both of these would be exactly the same. These vectors, for all practical purposes, are the same, given that they have the same direction and the same magnitudes, the same lengths. This vector connecting points A and B has a direction. The initial point A is 0, 0. The final point B is 3, 4. So, for every 3 units this vector goes to the right in the positive direction on the x-axis, it goes up 4 units. That's a direction. 3 units to the right, 4 units up. That gives it a definite direction. Likewise, in the last example, I had a vector pointing northeast. In that case, that vector was a representation of a quantity that for every 1 unit it went east, it went 1 unit of distance north. That's northeast. That's a direction. So this vector has a direction. And it also has a magnitude. What is that magnitude? It's the length. What's the length? Well, we can use the Pythagorean theorem. And if you can't remember what the Pythagorean theorem is, which in all probability you don't, it's this. How does that help us find the length of this vector? Well, you see, if you look at this diagram representation, this is the hypotenuse of a right triangle. So we can find the length of this vector by completing the right triangle that is defined by this hypotenuse. So we can see that this vector is defined by the points A and the points B. That means that this length right here is 3 units. This length is 4 units because the vertical distance between these 2 points is 4 units and the horizontal distance between them is 3 units. So now we use the Pythagorean theorem to find the magnitude of this vector. We plug in the x value, one of the legs of this triangle with a hypotenuse that is the length of this vector. So we plug in 3 squared plus 4 squared is equal to the magnitude of this vector, which is labeled by something that looks kind of like an absolute value sign, but it's not an absolute value sign. That's the magnitude squared. So what do? We solve for the magnitude of the vector AB. In this case, 3 squared is 9. 4 squared is 16. You add those together, what do you get? You get 25. You get 25. Shut up. Anyway, you take the square root of 25, you solve for AB, what do you get? The square root of 25 is 5. The length of this vector is 5. That is the magnitude of my vector. So how do we notate this vector mathematically? Well, we use an ordered list of numbers. In the case of this vector, this is in 2 dimensions. It doesn't come out of the board, it doesn't go in the board, it stays on the board. It's in 2 dimensions. So how do we notate? How do we notate this? Well, we need an ordered pair. We will represent that as 2 numbers separated by commas in brackets. What are these numbers? They're distances along axes. So the numbers that we put in for this ordered pair are the distances that this vector projects along the respective axes. So how far does this vector project along the x-axis? Well, as we've already shown, it's a distance of 3. So the x component of this vector is 3. How far does this vector project along the y-axis? Well, if you look at its projection along the y-axis, that is a distance of 4 units. So that's my y component. I plug in 4 as my y component. And that 3, 4 in brackets is my vector representation. Mathematical notation for a vector. But Professor Rage, how does that notation represent direction and magnitude? Look here at this vector notation. This vector notation tells me that from an initial point, which isn't a specific point in space because vectors don't have a location, they only have magnitude and direction, they don't have a specific location. But this notation tells me that from any point, initial point A, this vector goes down 3 units, -3, or it goes to the left, -3, that's the x component. It goes to the left 3 units, because it's negative on the x-axis, so it goes left 3 units, and then it goes +5 in the y direction. That's the y component. +5 is the y component. So that's 1, 2, 3, 4, 5 units. And that is where I place my final point. That's what this notation tells me. It tells me what displacements I go from an initial point. And then I draw an arrow. And that is this vector written in a diagram format. Given this notation in 2 dimensions, there was only one way I could draw this vector. this notation defines a specific vector that cannot be drawn any way else. It goes to the left 3 units, goes up 5 units, and that's where the last point is. That's the final point. And I draw an arrow to that point. There's no other way I can draw that vector given that notation. Therefore, this notation gives me a specific vector that has a magnitude and a direction. So what if I want to represent a vector without the comma bracket thing? Am I screwed? No, I'm not screwed. I can represent a vector as a length and an angle that specifies the direction of the vector. And that angle will be the angle that the vector makes with the positive x-axis, the positive portion of the x-axis. So say I have a vector, -5, -12, represented by this illustration right there. That is the vector. That is a representation of the vector -5, -12. How do I find the angle this makes with the x-axis? Because finding this angle is the first step to representing this vector without this notation. I need to find the angle that this makes with the positive portion of the x-axis so that I can define its direction without using this bracket notation. So how do I find that angle? Well, first, in order to make an angle that I can solve easily, I need to shift this vector so that the initial point, the tail of this vector, is at the origin. So I'm going to do that first. So I draw the vector. That's still -5, -12. It's the same vector, I just shifted it over here. Same magnitude, same direction, same exact notation, same vector. Now how do I find the angle? Well, we have to use trig functions. You probably don't remember anything about trig functions, so let's review that. SOHCAHTOA, everyone's favorite trigonometric mnemonic device. Now, the one that really concerns us is this one right here. Because what this tells us is that in a right triangle, the tangent of an angle is the opposite side over the adjacent side. TOA. The tangent of an angle in a right triangle is the opposite side over the adjacent side. Now, how does that relate to this problem over here and finding the angle this makes with the positive x-axis? Well, given that the notation for this vector is -5, -12, we know that this distance right here, the horizontal projection of this vector is -5 units, right? But for the purposes, we want to essentially find this angle, which will help us ultimately to find the angle that it makes from the positive x-axis. But the first step to doing that is finding this angle right here. So how do we do that? Well, first, we see that this length, if we're to make a right triangle out of this vector, we'll draw a leg here, and we'll draw a leg there. This leg has a length of 5. This leg has a length of 12. Now, that's the right angle. So we have created a right triangle from this vector, where the hypotenuse of this triangle is a vector. Now, this angle is solvable. We can find this angle. How? Using this relationship. This is a right triangle. So we can say, this is the angle that we're trying to find. This angle between the negative portion of the x-axis and the vector itself. So we say, tangent of that angle is equal to, well, what's the length of the opposite? 12. What's the length of the adjacent? 5. So we know the tangent of this angle is 12 over 5. Now, we have this relationship. How do we isolate theta? You use the inverse tangent function. So what I do is I take the inverse tangent of both sides. And if I take the inverse of a function, the function cancels out. It eliminates. Because the tangent, the inverse tangent of tan theta is simply theta for a given set of angles. Now, I take the inverse tangent. What do I get? Theta is the arctan of 12 over 5. What is the inverse tangent of 12 over 15? Well, you probably can't do this, but I'm going to calculate this in my head. I get 67.4 degrees. Theta is 67.4 degrees. Okay, so we know this angle right here, that is 67.4 degrees. Okay, but that's not the end of this question. The question was to find the angle that it makes with the positive portion of the x-axis. And the convention that we have for defining angles with respect to the positive portion of the x-axis is to start from the positive portion of the x-axis and rotate counterclockwise until we reach the arm that creates our angle. In this case, the vector. So we start from the positive portion of the x-axis, rotate counterclockwise, and we eventually reach our vector. And that angle that we swung out in the process of swinging out to reach that vector is going to be the angle for that vector. So what is that? Well, we found that this was 67.4. So now we know this angle right here, this semicircle, is 180 degrees. So what we do to find the total angle, this angle right here, is we take 180 and we add it to 67.4. And what is that? Well, this is obviously a very complex calculation, so I'm going to perform very complicated mathematics and I'll get the answer. Okay, so I've performed very complicated mathematics, and I can now tell you that this angle right here is 247.4 degrees. That's my answer. That's the angle that this vector swings out, starting from the positive x-axis and going counterclockwise. That gives me a specific direction for this vector in a two-dimensional plane. Now, how do we find the length? The magnitude of the vector? Well, we use the procedure that we used last time. Like we said, -5 was the x component, negative 12 was the y component. Okay, so to find the length, we do what we always did. We use the Pythagorean theorem. So we treat this as the length of the hypotenuse, this length right here. We'll just call that L squared, or we'll just L. And we will now plug that into the Pythagorean theorem. What do we get? We get 5 squared plus 12 squared is equal to L squared, where L is the magnitude of the vector in question. Now, I'm going to perform some very complex mathematics again, and I'm going to get the answer. And the answer is L is equal to 13. Yes, that's exactly it. L is equal to 13. Very complex mathematics. You probably couldn't do that if you tried. So, we have now found the length, 13 units, and we had the direction, approximately 247 degrees. So now, what we have is a direction and a magnitude. 247 degrees, standard position. Standard position is just another way of saying we started from the positive x and swung out the angle counterclockwise. That's what standard position is. 247 degree standard position, a magnitude of 13. That is a direction, and the angle, scratch that. This is the magnitude, and that angle was the direction. So I have found a way of representing this vector with the magnitude and direction and not bothering with the bracket notation. Granted, you still have to use the bracket notation in some cases. Say I have a particle. It's moving in 2 dimensions. In this, we'll call the chalkboard the xy plane. It's moving in 2 dimensions, and it has a velocity. The velocity is 3,4 meters per second. This notation tells me that this particle is moving to the right at 3 meters per second and moving upward in the positive y direction at 4 meters per second. The components, these are the components telling me the respective components of the velocity. Now, if I have a displacement, just take this for an example. So I have a particle that moves from here to here. How can I tell how far that particle traveled? Well, we can use the Pythagorean theorem, where that's the x component, and that's the y component, and this distance is what we're looking for. So we just use the Pythagorean theorem, a and b, and we're solving for c. That's how I find the distance. This is a very similar situation, except I'm just dividing all of these quantities by a unit of time to get a rate instead of a distance. So how do I find the overall speed of this particle given the components? I use the Pythagorean theorem. 3 squared plus 4 squared is equal to the speed squared. So what is the speed? Five meters per second. My particle is going 5 meters per second. I'm done talking about vectors.